from Ilya.
Hi, thanks, Barry. So I have a few questions for Semyon, actually. So, Semyon, you here? Okay, great.
Yeah.
So let me start with the following question. So just to clarify my understanding. So do I understand correctly that what you've done so far is only for the abelian Laughlin states?
Yes.
So rephrasing this, sort of technically speaking, I mean, what's the input for your calculation? Do you need explicit wave function to be able to do anything, or is somehow other set of data?
Yeah. No, I don't need explicit. That's the beauty, that I do not need explicit wave functions. I need only wave functions on the plane. So if you give me planar wave function and you explain me what are the interactions, for example, you say it's a two-body wave function with 0 on the diagonal to the power beta, like a Laughlin state. Can you hear me?
Yeah, I can hear you. But I mean, the practical question is, suppose you want to repeat this for Haldane Rezai, or I don't know, read Rezai states, or whatever. I mean,
for example, we have a three-body states like read Rezai, or maybe even just Jack polynomial states of Bernoulli-Haldane, right?
Mm-hmm.
So you could try to. You don't have to know these states on a torus homogeneous surface. You don't have to construct them explicitly. You can use this technique of Grothendieck to compute these Chern characters without actually constructing the states in terms of, I don't know, theta functions or whatever. And you don't actually need to compute explicitly the Berry curvature, which is very hard computation because it's n-dimensional integrals, right? You maybe can do it on a computer for some number of particles. Mm-hmm. So you just need to know just a representative in the cohomology class. You don't need to know the Berry curvature itself in all detail. That's
so this is the future direction, so to speak. You can sort of go on and
yes,
continue.
You can definitely the Chern characters for all quantum Hall states are waiting there to be found.
All right. Okay. I have a more physical question though. So when you said that you could deviate from the center of the plateau and go to the place where you have some movable quasi-particles, I mean, you seem to be able to obtain something from your theory, even though I would naturally assume that this is something related to energetics, actually, because I mean, how do you liberate quasi-particles? It becomes favorable because of the energy. So, but your theory has no energy input whatsoever. So I'm confused about this point. So how does this?
We say that at the center of the plateau we were in a Laughlin state with fixed quasi-holes, period. So it's a very restricted Hilbert space. And when we increase magnetic field, we transition from this Hilbert space. We are no longer there. We have too much flux to accommodate.
But that's sort of an assumption that the resulting holes are movable, right? I mean, so you're not predicting any widths of the plateau, for example. You cannot predict the widths of plateau from your theory. Where it happens, you cannot say, right?
You know, to be honest, we have an explicit formula, but we did not thought out all the consequences of this formula yet. This is one consequence, immediate consequence, where you compute Hall current and conductance, and you see what happens. You compare it to the literature, and this formula for the correction of to the Hall conductance, it was in the literature for on the plane. So our formula agrees with this literature formula for the correction of to the Hall current as you leave the plateau. So, but this is one small consequence of, and which uses only first-Chern class. We have higher Chern characters, all the Chern polynomial. We have to think out what else could we extract.
No, but I'm still surprised that no energetic considerations come into play here. It's strange. I don't know.
Could you show your formula again, please?
Say it again.
Could you show the formula again that you?
All right. So this is the formula for all Chern characters for the full many-body Hilbert space, meaning you have P quasi-holes which are not localized. If you set P to 0, you are back to pure Laughlin with quasi-holes localized. In this case,
there's an abstract formula. How do you compute it, though?
So this is a this is a numerical coefficient. This is the binomial coefficient. G is genus. M is number of this Chern class. Beta is inverse field infraction. N number of particles. P is this number of. So all these are just implicit numbers which you can use. N equal to million. P is equal to 10. Genus 5. I don't know.
So this is counting just some dimension of the Hilbert space, or what?
When M equal to 0, it counts exactly the dimension of Hilbert space. When M equal to 1, it counts the first Chern class. When you divide it by dimension of Hilbert space, you get whole conductance. So whole conductance, first Chern class divided by dimension. But you have second Chern class. So
no, but all this assumes some gap, right? I mean,
this assumes a gap, yes. Yes.
So, but the question is,
we're in the space of holomorphic polynomials.
Yeah.
We do not leave to the higher Landau level. That is.
No, it's not about the high Landau levels. It's about when the.
Well, yeah, we don't break the gap. Yes, yes.
Mhm.
This assumes that the dimension stays constant as we move along our parameter space. That is.
So this is for a Hamiltonian with a null space, then.
Yes, but Laughlin state there is a unique Laughlin state on a plane, but once you take it to the homogeneous surface, you get this degeneracy. You get this null space, which is so for pure Laughlin state is dimension beta to the genus. So for torus, you and Rizai predicted beta states, and this is exactly if you plug genus 1, M equal.
But there's no impure. You haven't put any any kind of potential to localize quasi-particles or anything.
No, it does not. When I say localized quasi-particles, I just mean the states which are of this form, that there are zeros at some points.
Yeah, but you need a potential to force the quasi-particles to stay at those points when you change the boundary conditions. Yeah,
this is a condition that I impose. I say that I fix these points with a nail. All that I move my parameter space, but these points stay fixed as I change the fluxes. So this is a initial setting.
So, and delocalized quasi-particle simply means that your symmetric polynomial has a given number of zeros, or what's the...
Right.
Okay.
Exactly. Thank you. Yes. I say delocalized quasi-holes. I mean just any state which is a symmetric polynomial of degree up to some p.
Well, this is the equivalent of having a Landau level with no degeneracy lifting. So of course, you need to put something in that will actually cause the quasi-particle, energetically localize the quasi-particles.
Right. But that I put it in by
hand.
By hand, yes.
Okay.
Exactly.
Thank you.
Right. Thank you.
Okay.
Right, thank you.
Great. So next question we have is from Semyon.
Hi, I have two technical questions for Professor Zaletel.
Hi.
So in your IDMRG calculation, do you put some cutoff on the Coulomb interaction? And the second question is that if we replace the Coulomb interaction with some short-range interaction, will there be any qualitative difference in the results?
Yeah, so the actual interaction we use, it's 1/r, but then because we're on a cylinder circumference, we eventually, to do the scaling, we have it decay exponentially beyond a distance of like half the circumference.
Mm-hmm. Mm-hmm.
But I think the whole argument would go through even if it was just 1 over r to all distances. It's just that's a little perverse on the cylinder. If you made it short range, like, you could just make the exponential decay even faster. The superconductivity would just be stronger for the obvious reason that the charges aren't repelling each other as much. So it would work with short range as well. You'd get even better energetics. It's just the 1 over r, in most experience, is at least what you have up to the gate distance. So that's what we used.
I see.
Yeah, thanks.
Okay, and we have a question from Dima.
So I have another question to Semyon, and that's actually a crazy question. I don't know if it makes much sense what I'm going to ask, but you worked with Chern classes, which is entirely natural because you have a complex vector bundle. But in principle, there are many other characteristic classes. And I wonder if some settings, say some symmetry or something else, would make it meaningful to consider them in place of the Chern class. Does it make sense or it's entirely crazy?
Nothing comes to mind immediately, but it's totally possible to imagine a situation where you have not a complex vector bundle, but in quantum Hall we naturally have all these states. They are complex vector bundles. So maybe in some different physics situation. Nothing comes to mind immediately, but
so maybe you impose some anti-unitary symmetry or something, and so restrict your bundle to be real, something like that. I don't know if it makes sense.
So we are not in some sort of quantum mechanical setting where it's wave functions, but something.
No, it maybe it's wave function, but it has to be real wave function because of the
real. Oh, there may be techniques which allow to compute such things mathematically when it's a real wave function, real bundle. But do you have something in mind?
No, it was a question to you. I saw that you explained such subtleties of this particular characteristic class, but obviously the theory of all characteristic classes is very similar, be it Chern class or anything else. And so I just wondered, maybe you thought about that. Maybe there is some setting where, say, it's even Stiefel-Whitney class. Maybe you can perhaps you just look at some very crude information and forget about wave functions even. Maybe there is something there just to look even at that.
Maybe I can ask you the question then. What would be the meaning of a Chern number or Chern class higher than 1? Do you have a physics?
So sorry, meaning of what?
For example, second Chern class or higher Chern class. What would be the physics meaning? I know in Young-Mills theory there is a second Chern class of instantons in Young-Mills theory have second Chern class. Skyrmions, which Mike mentioned, they also may have higher Chern classes. But what would be
I don't know. I must. I completely crazy things. I just thought that since you think about that, maybe you can tell something. But if it's all crazy, then forget about that.
I don't think it's crazy, but it just I didn't think about it. I don't think it's crazy at all.
Okay, thank you.
Okay, so I think we're actually just about on time now. I don't see any more hands raised, so we can turn things over to the final session of the day.